All right, so today's lesson is on quadratic inequalities with two variables. Yesterday we looked at quadratic inequalities with only one variable, so there was no y involved. But today we're going to throw y's in here, see how that changes things. So today's plan is we're going to start with a review of interval testing and quadratic inequalities with one variable. That's what we did yesterday. We're going to introduce quadratic inequalities with two variables today. And then I'll throw in a word problem at the very end today, although I'll give you a little heads up. The word problem has more to do with the stuff that we did yesterday on interval testing. And then, of course, you guys all have practice time. Perfect. Now, another thing you can kind of celebrate, today is it. After today, we've actually completed the entire Math 20-1 curriculum. So by the end of today, you have learned every outcome in Math 20-1. So it's all review from here on out. It's still very important, though, from here on out to keep up and review the previous material we've covered. Of course, once we clear through this unit, we're going to have some time to review the rest of the course. But anyway, enough rambling. Let's get going. So with interval testing, very first question right out the gates, solve the following quadratic inequality algebraically. If you feel up to it, I'd appreciate if you pause the video here and give this one a try on your own, and I'll go over it in just a second. All right, so I'm going to go over this now. Hopefully you were able to give it a try. If you weren't, though, if you feel like you're still learning, that's fine. We'll move everything over to one side. So I'll minus 6x and I'll minus 7 over to bring everything over here with the x squared. So x squared minus 6x minus 7 needs to be greater than 0. Now, the next step, of course, is to find our critical point, which is the points we had as x-intercepts. So basically, you just have to factor this. So we're looking for two numbers with a sum of -6 and a product of -7. Well, that would be -7 and +1. So we'll say it's x minus 7 times x plus 1 is greater than 0. And then our critical points where that would be equal to 0 would be x is equal to 7 and x is equal to -1, because that would make each of these pieces, of course, equal to 0. We take these x-intercepts here and we test them using intervals. So I set up a table where I start with my smaller one, which is -1, and I'll say x is less than -1. Then I put both of them in the center. -1 is less than x, which is less than 7. Make that a little longer there. There we go. And then I check the bigger one by saying x needs to be greater than 7. Next thing we do is we just plug in some numbers that fit this criteria here. An x that's less than -1 would be, how about x is equal to -2? If you plug -2 into this quadratic right here, we're trying to see if it's greater than 0. In other words, we're trying to see if it gives us a positive number. If you plug -2 into here, you're actually going to get +9, which is, of course, a positive number, which tells us that this right here is going to be one of our solutions. Now, if we check the center one here, we're looking for an x between -1 and +7. I think a really good one to plug in, of course, would be x is equal to 0. If you throw x is 0 in there, you're going to see that you get -7 as an answer. And that, of course, is a negative number, which is not what we're looking for here, because we're looking for where it's greater than 0, not where it's less than 0. Last one here, x is greater than 7. The obvious number to plug in would be x is equal to 8. Did I say less than 7? X is greater than 7. I don't know what I said. Whatever. Anyway, plug in x is equal to 8 one way or another. If you plug in x is equal to 8 in there, you're once again actually going to get 9. And 9 is, of course, a positive number. So that is going to be one of our solutions as well. To finalize it, you should always make sure you list your solutions one more time to really solidify your answers. So the answer to this is x is less than -1 and x is greater than 7. And then you just put a box around it. Lets me know that you got it right. So again, that's a quadratic inequality with only one variable. So it's quadratic because there's an x squared, and there's only one variable because there's no y involved. So if you ever see a situation like this where you have an inequality with some quadratic in it, but you only have one variable in the whole thing, that tells you you have to use this interval testing. I'm pretty sure in every question I'll ever ask you, I'll kind of lead you towards that, say, hey, you got to use interval testing here. But it's still a good thing to know. So again, if you have a quadratic and only one variable in an inequality, you have to do this interval testing thing. So that begs the question, what do we do if we have two variables? And it's a quadratic, rather, I should say. Well, I want to remind you, just from a couple days ago, we looked at linear inequalities, linear, not quadratic, linear inequalities with two variables. What we did was we just graphed the line, and they were all straight lines because they were linear equations, or linear inequalities, I should say. And then we just had to figure out whether to shade above or below the line. Now, these, when you have a quadratic inequality with two variables, so an x and a y, and it's quadratic because there's an x squared in there, these actually work exactly the same. It's just that they're trickier because it's a quadratic rather than a linear line. Linear equations were really easy to graph. You just have to find your y-intercept and then use your slope to make a straight line. Quadratics were a little trickier. We'll start with the simplest quadratic though. X squared, of course, is based at the origin, 0, 0. We're looking for where y is greater than or equal to x squared. So what I would start with, just like before, is graph the stuff that isn't your y, right? So just pretend that this was an equation and you're graphing it. So like before, when we graphed a linear equation, so a straight line, we're just going to graph x squared this time around. Graphing x squared is actually quite simple. You can use your 149 rule based off your origin. Move over 1 and then up 1. Move over 2, up 4. Move over 3 and then up 9, hence the 149. And then just make sure you mirror it on both sides. And then we are totally good to go there. And here's one other thing. This is greater than or equal to, so we have to use a solid line. So using a solid line, we'll connect all these dots as best we can. That wasn't too bad. Let's try this side. This side's usually worse for me. Let's try, there we go. Not an art class, but we'll do the best we can do. There we are, that's our quadratic. That would be what we would do if it was an equal sign. Y is equal to x squared. But this is y is greater than or equal to x squared. Well, we got the equal to part out of the way. The greater than part, however, though, means we need a shade above the line. So once again, using that analogy I had the other day, imagine it's raining. If you are above the line, that means you're above the roof. So if this was some really weird roof, I guess maybe like the Saddle Dome in Calgary, then you want to be above that if we're greater than, right? So this area, shade all that in there, right? Because that is above the line. There you go. Anyway, so here's a quick reminder. That quadratic was relatively easy to graph because it was literally just x squared. If you have a more advanced quadratic, though, the easiest way to graph them is to use the 149 rule, which we kind of used on that one. But there's a little bit more to it when you have a more advanced quadratic. Step number 1 is make sure you have your quadratic in standard form. That's ax squared plus bx plus c. The other side should just be your y. Just make sure you have this all ready to go first. Then use a little formula, and this is not on your formula sheet anywhere. It's part of your quadratic formula, so technically I guess it's kind of on your formula sheet, but it's not explicitly given. X equals negative b over 2a. This allows you to find the x coordinate of your vertex. Then plug that x into your equation to get your y coordinate, and then just graph that vertex. That's always going to be your starting point, getting the vertex of your quadratic. From the vertex, go right 1, then up 1a, so 1 times a that is, and then go back to the vertex, go right 2, and then up 4 times a. Then go back to your vertex and then go right 3 and then up 9 times a. So it's just the 149 rule. Sometimes you can even expand it to do 16a and then I guess 25a after that. I don't think I've ever done that, but basically you're just following the path that a square goes, right? 1, 4, 9, 16, 25, so on. Now for step 4, it says repeat step 3 except to the left instead of the right. Honestly, it's probably easier for all of us to say mirror it. So in other words, just flip it over and then you're good to go. All right, so here's a more typical kind of example. Graph the following 2-variable inequality by hand. In other words, no graphing calculators needed here. So since it's a quadratic inequality and we got 2 variables, there's y and there's x's, that's where we actually put it on a 2-dimensional graph here. To graph this, because it's a quadratic, we should start by finding our vertex. Remember, the formula for a vertex is x equals negative b over 2a. So in this case, that'll be negative 6, so positive 6 over 2 times 3, which is just 6 divided by 6, which is just going to be 1. So x is going to be 1. We know our vertex is going to be somewhere along here where x is 1. Take the 1 and plug it into this. So we're going to have 3 times 1 squared minus 6 times 1 plus 1. And you're going to find that y is equal to negative 2. So our vertex is going to be 1, negative 2. So 1, negative 2 would be this coordinate right here. And then from that, we just use our 149 rule. So go from your vertex, go over 1, and then up 1 times a. Well, a in this case is 3, so we have to go up 1 times 3, which is 3. So 1, 2, 3. Then you go back to your vertex, go over 2 points, and then up 4 times a. Well, 4 times 3 is 12, so we have to go up 12 points. From negative 2, that'll take us up to positive 10. And I think it's pretty safe to say in this case, we're not going to be able to do the 9 part of the 149 rule because we're going to be way off the chart. So just flip this, make sure it's mirrored on both sides. And your graph's going to look something like this. Now I want you to notice it's y is less than or equal to this. Since there's the or equal to portion, we actually have to use a solid line here. So the solid line is going to go up through here. Do your best to graph it. Might have to just kind of lift my hand off the thing here. There we go. And graph this side as well as this side over here. Ooh, that's going quite off. Let me try to fix that. There we go. It's getting a little bit better. Swerve a little more this way. Yeah, it's not perfect, but you know what? It'll do for what we got to do for this. So that's the if that was equal to it, right? So we've graphed the quadratic now as if they were equal. Now we want to shade below this quadratic. Now here's what's kind of weird. Again, if you imagined this as being some sort of roof, like once again, like a saddle dome, we want to shade underneath it. Well, the weird thing about this is like 90% of the graph is going to be underneath this. Anything that is like on this side, or even down here, or even over here on the right, that's technically underneath the graph, right? So that means we have to shade pretty much the majority of this graph. So I'm going to be kind of sloppy with this. Just make it very obvious what part of the graph you're actually shading. But yeah, that's pretty much about as good as I can do on this one. So it doesn't have to be perfect. Definitely don't take the time to literally color in the entire thing, but just make it pretty obvious what side of that graph is actually being colored in. And if you do the lines kind of at an angle away from your graph, it really makes it like pop out and looks a little bit better. Anyway, we've got one more that we're going to graph here. There really wasn't all that much to this lesson. The word problem is probably going to give us more trouble than anything. Solve and graph the following inequality by hand. X squared plus 10 is less than negative x, or negative 8x rather, plus y. First things first on this one, we should get our y all by itself here. So I think we should maybe add 8x to both sides here. So that's going to give me x squared plus 8x plus 10 is less than y. And I don't know about you, but I really don't like having it where y is on the right-hand side. So I'm going to like flip everything over. Remember, think of this inequality as a mouth that wants to eat the bigger number. So why don't I say y is greater than, the mouth is still facing the y, x squared plus 8x plus 10. I didn't change what it was, I just changed the way it was written. Anyway, so we can start this by, of course, finding our vertex. The vertex is going to be found by using the formula x equals negative b over 2a. In this case, that'll be negative 8 over 2 times 1, which is going to give us negative 4. If you plug negative 4 into your inequality right here, you're going to find that y is equal to negative 6. So if you plug negative 4 in here, you'll actually get negative 6 as your y, which tells us that our vertex coordinate is negative 4, negative 6. So I'll start by graphing that. Negative 4, negative 6, that's about right here. Plot that there. Then we use our 149 rule to draw our quadratic. Starting at the vertex, you go over 1 and then up 1 times a. Well, 1 times a in this case is just, well, 1. So I'll put a dot right there. Go back to your vertex, go over 2 points and then up 4 times a. Well, that's just going to be 4, so that's going to lead us to here. Then go back here, go over 3 points and then up 9 times a. 9 times a in this case is going to take us up here to 3 because negative 6 plus 9 is positive 3. And just for fun on this one, we could actually do 149, 16. So you can go over 4 spots from your vertex and then up 16 times a. And 16 times a in this case is 16 times 1, which is just 16. Negative 6 plus 16 brings us up to positive 10, so right on the limit of this, this window we have here, but still something that might be useful for helping us more accurately draw our graph here. Flip it on both sides, make sure this is now totally mirrored. There we go, and there we go. And now the next thing we should check is, are we going to do a solid line or are we going to do a dotted line? Well, notice in this case, it's y is strictly greater than this quadratic right here. And because there's not an equal sign, we're not going to do a solid line. We're just going to do a dotted line, which actually with my situation, I'm going to actually prefer here. This is quite nice. So just do a dotted line and just make it pretty clear where your dotted line is going to go. If you prefer doing a dashed line, that's fine. It's all the same kind of idea, just as long as it's not a solid line and that it's very clear that this is just a dotted line. There we go. All right, last up, we have to shade the appropriate side. Notice it's y is greater than this. Greater means above. So if we're going to shade above this line, that means we're going to be shading all of this section in here. So be really careful what side of your graph you are shading. because that's a common mistake. A lot of people seem to shade the wrong side of their graph. And that's all you got to do. That's it for graphing these inequalities, right? So if you have two variables, you're going to use a two-dimensional graph. In other words, you're going to use, well, a Cartesian plane, okay? Last problem of the day, it's a word problem. This is going to seem more like stuff from yesterday than today, and you'll see why in just a moment. The length of a rectangle is 2 centimeters greater than its width. The area of this rectangle is at least 20 centimeters squared. What are the possible dimensions of this rectangle to the nearest tenth? Now, just someone who's a little bit more practical, you could just automatically shout out some answers and say, oh yeah, that works, right? We know the length is 2 centimeters greater than the width. So it's just the width plus 2, basically, right? And we know the area of the rectangle is at least 20 centimeters squared. You could throw out a crazy number. You could say, you know what, the length is, I don't know, 102, and the width is 100. Well, 102 times 100 is like 10,200. So clearly that's more than 20 centimeters squared. Look at us, we're done, we can go home now, right? That's not how these questions work. Questions asking for what are the possible dimensions. That's implying what are all of the possible dimensions. In other words, we need to solve this using an inequality because there's going to be a whole range of possible answers, not just a single one that we just pick out of a hat. We have to find all of these answers. So to do this, we have to be a little bit more creative. I'm the kind of person who prefers to draw a picture before I get started on this. If we have a rectangle where we know the length is 2 centimeters longer than the width, why don't we say that this side is the width and this side is the length, but we might as well say the length is just the width plus 2 because it's 2 centimeters greater than the width, right? If we have it like this, we can only deal with one variable this time. We don't have to worry about length. We just totally ignore it. We got width and width plus 2. That's all we got to worry about. The area of a rectangle is just length times width, so we can say it's width times width plus 2. And we know that that is at least 20 centimeters squared. So it theoretically could be 20 centimeters squared, or it could be more than that. So we could say that this, width times width plus 2, that's the area of a rectangle, is greater than, or possibly equal to, 20. This is going to help set us up to find an inequality. And rather, it'll actually even be a quadratic inequality because the w is going to double dip through here, and you're going to have w squared plus 2w is greater than or equal to 20. If we bring all that to one side, you're going to see we have w squared plus 2w minus 20 is greater than or equal to 0. This is just a quadratic inequality with only one variable, right? We don't have like another y or something over here. So that means we have to use our classic interval testing that we learned yesterday. In order to do interval testing, though, we need to know what the theoretical x-intercepts would be. You could try using the sum product rule on this one. You could say two numbers with a sum of 2 and a product of negative 20. You could try that pretty much all day long. You're going to find that you're going to really struggle to find those. So unfortunately, just like that one question we did yesterday as well, we're going to have to bust out the quadratic formula. Just as a reminder, even though it is on your formula sheet, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Of course, we give you that on the formula sheet. There's no way you'd ever have to memorize that. Even I have a hard time sometimes remembering what it was. But bottom line is you just plug in all the numbers into there. So x is going to equal negative b, so that'll be negative 2, plus or minus the square root of b squared, so 2 squared, minus 4 times a is 1 in this case, times c, which is negative 20, all divided by 2 times a, so 2 times 1. I'll spare you the details of simplifying this thing down. Usually, like, you could do that, especially if you were looking for an exact answer, but we really don't care this time around. We are just trying to solve this to the nearest tenth. Let's just punch this into our calculator. If we do the positive one, I always call it x positive. So if we went negative 2 plus all this, you're going to get as an answer 3.6. Once again, just rounded to the nearest tenth. However, if you subtract this, so negative 2 minus all this, you're going to get negative 5.6. Now, I'm going to be honest with you. I'm going to totally level with you here for a second. These are usually what we would use in an interval testing environment. So in other words, you go, okay, x is less than negative 5.6, and then you go negative 5.6 is between x and 3.6, and then you go x is greater than 3.6. By all means, you could do this. But let's just take a step back here for like just a brief moment and just think logically about this. What is x, or I guess in this case, we really should call it w. What does w represent here? W represents the width of this rectangle. Does it make sense for us to have a width that's less than negative 5.6? That's not even a rectangle at all. That's a negative width on a rectangle. That makes no sense at all. So this is a nonsense answer, which means this entire interval, regardless of whether it gives us what we would want, is total nonsense. Furthermore, more than half of this interval is nonsense because an x that's less than 0 just doesn't make any sense at all. So it's like this whole segment of it right here doesn't even need to be considered. Now, lastly, as if that wasn't enough, it's kind of silly to even plug anything in here because x being our width, if it was less than 3.6 and we're looking for where the area of this rectangle is greater than 20, what on earth would make us think that a small width would give us an area that's greater than 20, right? That's not going to work. So just logically, I can deduce without doing a single calculation here that x is greater than 3.6 is going to be our solution. If you would prefer to do it the old-fashioned way, by all means, plug a number in. You could even do all three of these, right? Just please don't consider the one that's a negative, right? Use a little bit of common sense on that one and say, wait a minute, you can't have a negative width. That makes no sense. So if you wanted to plug anything in here, you could maybe plug like x is equal to 1 into this. And remember, x is really w, so maybe I should call it that. W is equal to 1. You're going to find that it's just 1 squared plus 2 times 1, so that's 3. 3 minus 20 is negative 17. That clearly doesn't work, right? So it's not going to work. This one's not going to be a valid solution. But if you plug in an x that's greater than 3.6, so how about like 4? You're going to get 4 squared, which is 16, plus 2 times 4, which is 8. So that brings us up to 24. 24 minus 20 is 4. 4 is greater than 0. What do you know? X is greater than 3.6, or in other words, W is greater than 3.6. That is going to be your range of widths. Now, I guess it does say what are the possible dimensions. So we have to include our length as well. Well, length is just 2 centimeters more than the width. So we have to say length or width is greater than 3.6, and therefore length is greater than 5.6. That's supposed to be a point. There we go, 5.6. That's about it, okay? Don't go too crazy on this. Oh, I totally forgot something. Some of you guys are probably just shouting at the screen. You got to go or equal to, because again, it was or equal to here. Whew, almost missed that one. Anyway, we're done. That's it. So for practice, homework booklet. You can now complete the entire thing. It is due on Wednesday, January 13th, when we are back in class. If you have a printer, of course, hopefully you printed it off. Otherwise, just do it on a piece of loose leaf and then transfer your work over when we return. Other than that, though, page 496, questions 1 AC, 2 AC, 3 to 5, 6 AC, and 7. I want you to do those. Anyway, you know where to find me. Best of luck.